Because molecules have dipole moments, like this HCl molecule, which has a dipole moment that goes positive on the hydrogen end and negative on the chlorine end, the hydrogen is partially positive and the chlorine is partially negative. We know that negative charges attract positive charges, and so if I have a bunch of HCl molecules, I would expect that they would try to align themselves such that the negative end interacts with the positive end of another molecule and the positive end interacts with the negative end of another molecule. So plus to minus, plus to minus, plus to minus, and the HCl molecules are going to arrange themselves and align themselves so that that interaction can occur. Remember that that is an attractive interaction, and attractive interactions lower the energy of the system. The lower the energy of the system, the more stable the system will be. And so we're going to end up with the most stable, lowest energy system when we can interact these separate molecules such that the negative end and the positive ends are aligned with each other. We call this type of interaction an intermolecular force, because there is a force between the molecules, between molecules, a positive-negative interaction or force. We sometimes abbreviate this as IMF for intermolecular forces. This example that we've just looked at is one particular type of intermolecular force, and we call this a dipole-dipole interaction because it is an interaction between two dipoles. So clearly molecules that have dipole moments can interact with one another. But what about a molecule that doesn't have a dipole moment, like Cl2? Both chlorines have the same electronegativity, and so there's no dipole moment in Cl2. So we might imagine that this is a completely nonpolar molecule, which it is, and that there would be no reason for the two chlorines to interact with two chlorine molecules, Cl2 molecules, to interact with one another. If we look at the charge distribution, we can see that it's pretty evenly spread throughout the molecule, and that there is no net dipole moment in these molecules. However, it turns out that when you have a collection of chlorine molecules like this, Cl2, 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 that they can induce dipoles in each other. So let's imagine how that might work. So if I have a chlorine molecule, these chlorines have a lot of valence electrons that are relatively loosely held to the nucleus because they're out in n=3 shell. So even though we draw them as though they are completely associated with this chlorine atom, these lone pairs with this chlorine atom, and these lone pairs with this chlorine atom when we're drawing Lewis structures, in reality, all of these electrons are shared to some extent throughout the molecule. And so I could imagine that if another chlorine approaches this chlorine molecule, that the electrons in this molecule will push these electrons away, and so push them more towards this side of the molecule. And so what might happen is that we might end up getting a chlorine with more electrons over here and less over here, because this chlorine molecule has pushed its electrons closer to this chlorine, and so now I end up with a partial negative charge over here and a partial negative charge over here, and a partial positive charge over here, and a partial positive charge over here. Now, that situation is not going to stay like that, because as soon as this chlorine molecule moves away from this chlorine molecule, this is going to relax back to this nice even distribution and be nonpolar again. So these dipole moments, these little dipole moments that are induced in a molecule, are only there instantaneously, only for the amount of time that this chlorine spends near this chlorine. And so we call these instantaneous dipole moments because they don't last for very long. When we have these instantaneous dipole moments that are induced in a different molecule by a molecule that's near it, we call all of these kinds of interactions where we have instantaneous dipole moments that are induced by another molecule, induced dipole, induced dipole, induced dipole, induced dipole interactions. And any interaction between molecules that involves an induced dipole, so we could have dipole, induced dipole. So we could have a molecule with a dipole inducing a dipole in a nonpolar molecule, and that would be another type of induced dipole interaction. All of these things collectively are called London forces. Notice that all of these types of intermolecular forces rely on a plus-minus attraction. And remember that that attraction depends on how big the charge is, how much charge you have. So larger charges, larger plus or larger minus charges, lead to stronger forces. So the more positive charge or the more negative charge you have, the stronger you expect that intermolecular force to be. So that leads to a hierarchy of intermolecular forces from strongest to weakest. So let's start with the strongest. Something we didn't talk about is that we might have two ions in solution. So let's imagine a nitrate anion and an ammonium cation in solution. So we have these in solution, and you can see that this has a full minus charge and a full plus charge. And then we would expect that these guys would interact with one another and sort of stay close to each other in solution because they're attracted to each other. And so this is an example of an ion-ion interaction, and that's one of the strongest types of interactions that we can have. Next, we have dipole-dipole interactions, which we talked about first. And here we have partial charges, but those partial charges are permanent on the molecule. So our example was HCl, which has a dipole moment like this, and we would expect another HCl molecule to line up with the plus near the minus and have that plus-minus interaction. But because these are not full charges, these are just partial charges, this is weaker than this interaction between full charges. So then lastly, we have our London forces, because those are interactions between partial positive and partial negative charges that are only instantaneous. They don't exist for a long period of time, and so they're very weak. Within each of these categories, ion-ion, dipole-dipole, and London forces, we can have stronger or weaker interactions of a given type. So the larger the charge, the stronger the ion-ion interactions will be. In addition, the smaller the ions are, the closer they can get to each other, and therefore the stronger the interaction is going to be. If we're looking at dipole-dipole interactions, the larger the dipole, so the stronger the dipole, the more that the positive and negative charges are separated from each other, the stronger the force is going to be. So this means that if you have two atoms with really, really different electronegativities, that's going to be a stronger dipole than atoms that have similar electronegativities. So stronger dipole, stronger interaction. And then when we have London forces, here what matters is how tightly held the electrons are to the nucleus and how many the electrons there are that can be moved around in that molecule. So larger molecules have more electrons that are less tightly held to the nucleus. And that means that they can move around more easily. And induce a dipole more easily. And so larger molecules with more electrons will have stronger London forces. There is one last type of intermolecular force that we need to talk about, and that is hydrogen bonding. Although this is not a full covalent bond, we call this type of force hydrogen bonding, but it's really an intermolecular force, not a covalent bond. It has some properties that are kind of like a covalent bond, but it is not a full covalent bond. It's not a full sharing of electrons. So what is a hydrogen bond? Well, really, it is a special case of a dipole-dipole interaction. So let's see how this works. If I have a hydrogen atom that is bonded to a oxygen, nitrogen, or fluorine, these are the only things that can participate, the only types of hydrogens that can participate in hydrogen bonds. So I have to have an oxygen, a nitrogen, or a fluorine with a hydrogen bonded to it in my molecule in order to have any opportunity to form a hydrogen bond. So what is going on here? Well, if we look at the electronegativities of these molecules, oxygen, nitrogen, and fluorine, they all have very high, some of the highest electronegativities. And so that means that there are difference in electronegativity between the atoms, oxygen and hydrogen, nitrogen and hydrogen, or fluorine and hydrogen is large. So there's a large difference in electronegativity. That means that we have a very strong, very large dipole moment for that bond. So now we're not talking about the dipole moment for the whole molecule, we're talking about the bond dipole moment here. So let's imagine that I have the following molecule. Which happens to be methanol. Here I can see that I have a hydrogen connected to an oxygen. That's one of the criteria that I have to have if I'm going to form a hydrogen bond. So if I imagine this with another methanol molecule, so let's draw another one here. I can see that I imagine that because this bond is so highly polar that this hydrogen has a really fairly large partial positive charge. It's really positively charged. And because it's really positively charged, and I have these electrons over here that are negatively charged, I am going to get an interaction between the positively charged hydrogen and these negatively charged lone pair electrons. So this is a directional interaction that has to do with the bond dipole, not the overall molecular dipole, but the bond dipole, and that bond dipole causing the hydrogen to be very highly positively charged so that it can be attracted to a lone pair of electrons. So 2 criteria for a hydrogen bond. 1, you have to have hydrogen attached to an oxygen, nitrogen, or fluorine. And these guys have their lone pairs. And so you have to have lone pairs that can interact with the hydrogen that is very highly positive.